Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss correction for finite mass of nucleus. Let's begin. According to Bohr's theory of atom, Bohr used postulates. In his postulates, there are one such postulate is that in that of atom, in the core of that of atom, it is a heavy as well as massive teeny portion which is called nucleus, and around that of nucleus electrons are revolving in such a permitted circular orbits, and the mass of such nucleus is more severe as comparison to the mass of an electron. In technically we call it as the mass of nucleus is infinity, but in actual practice there will be a finite mass of such nucleus. How we find out that finite mass of such nucleus, and then accordingly the expressions for energy level diagrams, or we can say the spectral lines, also changed. In Bohr's theory, the nucleus is considered to be at rest because of very heavy mass as comparison to that of electron, but in actual practice nucleus is having a finite mass, and both nucleus and the electron revolve with a common center of mass at point O. If the motion of the nucleus is taken into account, then it requires some correction in the frequency of spectral lines. Let us consider nucleus, mass of the nucleus capital M, electron, mass of the electron small m. And the separation between these two smaller. And there will be a center of mass through which nucleus as well as electron revolved. This is the center of mass. At point O, and it has angular velocity omega. Let us say nucleus is at a distance of x from that center of mass. Therefore, electron is at a distance of r minus x from the center of mass. At equilibrium condition, its mass distance of separation from that of center of mass, that is x, is equal to mass of electron small m, distance of separation from that of center of mass r minus x. mx is equal to mr minus mx, x is equal to first we separate the terms relating to that of x. Therefore, mx plus mx is equal to mr, whereas x has common, m plus m whole into x is equal to mr, or x is equal to mr divided by m plus m. This is equation number 1. Also, from that equation, r minus x is equal to mx divided by m, or r minus x is equal to m by m, the value of x small m into r divided by m plus m, the small m cancel out, r minus x is equal to m r divided by m plus m. Here we use the value of x using equation number 1 here. It is equation number 2. Next, these two masses now reduced, and at center of mass they have an angular momentum, that is the angular momentum of the atom about the center of mass. Therefore, total angular momentum L of the atom about the center of mass is given by total angular momentum L is equal to angular momentum of that of nucleus, that is moment of inertia into angular velocity. Here the moment of inertia, mass and distance square from that of center of mass, x square, angular velocity omega, plus for electron mass small m, square of the distance from that of center of mass, r minus x square omega. Here we use the relation angular momentum is equal to moment of inertia into angular velocity, whereas I stands for moment of inertia. Moment of inertia. The values of x as well as r minus x are put at m. The value of x m r divided by m plus m whole square omega plus m value of r minus x capital M r whole square is equal to m square r square omega divided by m plus m whole square plus small m capital M square r square omega divided by m plus m whole square. Now we take common term as small m plus capital M. We have m r square omega divided by m plus m whole square. Or we write these terms one m plus m, another m plus m cancelled, only one exists, that is m r square omega divided by m plus m. Next, therefore L is equal to small m capital M divided by small m plus capital M into r square omega, whereas that term is called the reduced mass mu r square omega, whereas mu is equal to m divided by m plus m, that is the reduced mass of electron. Equation number 3. First, we say that the nucleus at rest due to its heavy mass as comparison to that of electron. If we consider nucleus is at rest, then angular momentum is given by L is equal to m v r. Here we substitute v is equal to r omega. Therefore L is equal to m r omega into r. Therefore L is equal to m r square omega. Therefore we see that due to the motion of the nucleus, the motion of the nucleus, that a small m, mass of an electron, is reduced by mu, which is the reduced mass, and corresponding energy of electron, corresponding energy of the electron in nth orbit is given by the expression En now changed to, in place of m we just simply write the reduced mass mu e to the power 4th z square divided by 8 epsilon naught square n square h square, or En is equal to minus mu e to the power 4th divided by 8 epsilon naught square h square n square. This is a changed energy expression. For hydrogen atom, the atomic number is equal to 1. In place of Z we just write 1. In terms of wavelength, that expression write as nu bar. Nu is equal to c by lambda. So nu bar 1 by lambda. Therefore that energy expression also changes to in place of m we substitute mu e to the power 4th 8 epsilon naught square c h cube, as nu is equal to c by lambda. Therefore nu bar, here again c is divided, in that of denominator side there will be the term c, 8 epsilon naught square c h cube 1 divided by n1 square n2 square. Nu bar, that term Rydberg constant RH n1 square n2 square, where RH mu e to the power 4th divided by 8 epsilon naught square c h cube, that is the Rydberg constant, for reduced mass of hydrogen atom. Look at the expression that the reduced mass is inversely proportional to that of wavelength, and that reduced mass is somewhat less than that small m. It should be noted that since mu reduced mass is somewhat less than small m, then the wavelength of spectral line, the wavelength of spectral lines will be slightly more in case of very heavy nucleus. As mu when less than mass of that electron, reduced mass is less than mass of electron, then the wavelength of spectral line will be slightly more in case of very heavy nucleus. That easily understood from this particular expression. So, here with the help of this video lecture we understand the concept of correction for finite mass of the nucleus, as Bohr's postulates regarding atomic model suggested that the mass of nucleus is in infinity as comparison to that of mass of an electron. In that section actually that mass of the nucleus is finite, and we showcase it by taking the idea of reduced mass in case of two body problem. Angular momentum L, expression for energy now changed, and expression for wavelength also changed. Nu bar is the wave number. So, with this useful and informative notes, let me wind up the session. Thank you.